I'm here to introduce our presenter tonight, Fred Stoss, ADK member and University at Buffalo science librarian. Fred Stoss was trained in 2007 and 2010 by Vice President Al Gore to give Mr. Gore's climate change slide presentations. Fred has served Mr. Gore's nonprofit organization, the Climate Reality Project, as a mentor, assisting in the training of new presenters in 2012, including his daughter Katie, who's an earth science teacher, and in 2013. Fred will engage us with the most current version of Mr. Gore's Climate Reality presentation and include information from the original presentation that served as the basis for Mr. Gore's documentary film and books, An Inconvenient Truth and Our Choice, A Plan to Solve the Climate Crisis. He will add additional resources discussing climate change impacts to the Adirondacks and other locations in New York State. Please welcome Fred Stoss.
Thank you. Thank you for the opportunity to come. Denny and Nancy, absolutely delicious dinner we had tonight. I'd be remiss if I didn't say thank you for, as a German Lutheran, you know, dinners are important. That's why I married one. Sometimes I think that's why she married me, but regardless. When I was asked to do this, I was thinking last winter, we had a new concept or a new word that was added to our lexicon of environmental terminology, that infamous polar vortex. This is a picture of Niagara Falls that sort of froze during one of those sub-zero mornings. I wish I would have taken the picture, but I didn't. I borrowed it from whoever did. But it gives us a time to pause and think about what actually has been going on with our situation with our climate and how we get involved in doing these things. I have an undergraduate and graduate background in biology and zoology that sort of gravitated around the concept of ecology and environmental science, and actually started my research career at the University of Rochester Medical Center and migrated over to Syracuse University, where I was doing in those two places doing research in toxicology and environmental health, and got interested in data about toxicology and environmental health. And I can't say that I walked across the street at Syracuse University's campus, but I did walk across the campus to the School of Information Studies, where I ended up getting a library science degree. I started that about 35 years ago, and I've been doing that for over 32 years. So that's how a scientist becomes a science librarian. This is a pretty picture. There's a little bit of explanation about this. This picture was taken on Christmas Eve of 1968. It was I had just completed my freshman year at Hartwick College. And it was one of the Apollo missions that was sent up to find a place for a possible lunar lander with a payload of a person on board to land on this little structure here called the moon. This is the very first picture that was taken of the Earth with another planetary body in the foreground. And it was a prelude to that giant step. This, by the way, is the most reproduced photograph in history. It's in the public domain, which helps to make that happen, but it was taken from a NASA flight. Some people say it was the last picture that was taken by a human, because after that the cameras were all mounted and they were taken as a direction for automation of all the photographs. This is one of the very first satellite pictures of the Earth. And these pictures represented something that was rather interesting to this guy on the right-hand side, Al Gore. Who, by the way, he was the former vice president of this country. He used to introduce himself as one of the former president-elects. We know how that turned out. Went to Harvard. This guy was a librarian who went to Harvard. As far as the pedigree of degrees, that's where the similarities end. I became a librarian, and well, we know what he did. But some of those images is what sparked an awful lot of people to thinking about the position of the Earth and our relationships to it, going back into well before the 1960s and 70s. And in this particular situation, this is the little beast that we're going to talk an awful lot about tonight. Carbon dioxide, written sometimes like this or just like this. And we'll show you some graphs about where does the carbon dioxide come in terms of the fuel that we put into our cars and trucks and SUVs. It comes from making cement, from burning coal or natural gas, or gas flaring, which is what happens when you have a gas mine that you're not capturing all the gas, but you just you take the excess gas and burn it off. I used to drive by one. I'm Fred, and I'm a carbon sinner. I work in Buffalo, and I live in Rochester. My wife, Dottie, is my carbon offset. We live about 2 miles away from the University of Rochester Medical Center, where she works. So on the average, we're not doing that bad. So thank you, Dottie, for at least giving me some rationale for my carbon sin. So this little chemical has caused an awful lot of controversy. It's also produced an incredible amount of research. So I thought I would start with some current information that we're going to take a look at. Where does carbon dioxide, how do we measure it in terms of proxy indirect data? They measure things in ice cores, lake and river sediments, deserts, tree rings, pollen analyses of different kind of soil profiles. They measure things in ice and snow. And we have thousands of years. This goes back about 400,000 years. And these are cycles. I'll talk a little bit more later. But beginning in 1950, you see that this historical level has been about 300 parts per million. And right about now, we're up here at over 380. We're actually, last year was the first year we actually averaged was about 400.3. This is what we measure in the atmosphere in terms of our current record that's actually been measured. It started, for those of us, and I know that you're out there, because I can tell by the color of your hair, or the lack of it, can remember 1957 and 1958 as the International Geophysical Year, when Roger Revelle, who was a professor of Al Gore's when Al was at Harvard University, Roger Revelle talked with this one young scientist out of the Scripps Institute of Oceanography to start measuring carbon dioxide on a regular basis on Mauna Loa, Hawaii. And this is the record that generated from that. We've got some different pictures of that along the way. So if we take a look at from the emissions, this black line here represents the total emissions of carbon dioxide. A very good friend of mine, I used to work at Oak Ridge National Laboratory in the Carbon Dioxide Information Analysis Center. Greg Marlin is the senior scientist who started this inventory of going back and checking out all sorts of trade records and for being able to go back into the UK and other portions of Europe and such and trying to find out who was burning what types of fuel. And we see that after we can actually see where World War I was here, World War II. Wars have a nasty thing to deal with manufacturing and productivity, but these little dips in here. But after World War II, there's this monumental increase of carbon dioxide in our atmosphere. The amount that comes from solids, which is coal, is blue. The natural gas is here, oil, the liquids are here. And you can actually measure it in cement. And the gas flaring is this little gray line right there. If Greg can measure it, it's included in his inventory. But this is the one you want to pay attention to in terms of how much carbon dioxide is going into the Earth's atmosphere. They measure it in gigatons per year. I think we're up to right now about 5 to 6 gigatons of carbon per year going into the atmosphere. It's a lot. This is that data from Mauna Loa, Hawaii from 1957. The sawtooth kind of an approach here, it just has to do with biology. plants take in carbon dioxide, they give off oxygen. So every year when plants are in their growing season and they take in carbon dioxide, that graph will go down, and then in the dormant seasons of the late fall through the early spring, carbon dioxide will build up in the atmosphere until the process repeats itself. But this is a pretty steady record here that's maintained by NOAA. The Department of Energy has a significant component to that. Greg used to work at OR, and now it was managed by the Department of Energy. We're going to skip that graph. These are the 12 hottest years on record. Wow, they all look like the oldest is here. We have been facing this situation of warmer than normal wet weather for quite a while. 2013 was the 37th consecutive year with a global temperature that was above the 20th century average. How many of you remember February of last year? I think we had 3 or 4 actually really major snowstorms last year. We had temperatures that were well below zero. I have a friend of mine, she's a librarian at Saranac Lake, who every morning for about a week was saying it's at least 25 below zero, because that's the lowest number on her thermometer that was hanging out of the kitchen window. But this is the 348th consecutive month with global temperatures that were above the, this is half of North America was freezing. Last year was also the 4th warmest winter globally. Remember, one of the words that you have to mention in this, and make sure you emphasize it, is that it's global warming. If we take a look at where temperatures have been, this is some recent data from last year that takes a look at, by decade, those warmer years. And, so we go back quite a ways on this and saying that, well, we're still way above average. And if you remember your time scale, 1950 right there. Another temperature records that come from NOAA and NASA. 2 independently derived sets of data coming to pretty much the same kind of peaks and valleys. There's not very much, swing that shows us. One of the things that a scientist looks at is sort of like continuity and validity. When we start seeing the same patterns that are being measured, we can make pretty good assumptions that the data is pretty accurate and pretty viable in terms of the consistency with which it's done. When we give our talks, this thing about how they measure all that stuff was ice. Everybody wants to know about ice cores. So this is an ice core, right this little thing right down here. This is actually a hollow drill that drills down through a glacier. They have a big crane arm that's right here that suspends this thing, and there's a motor on the top that just very slowly drills down to whatever depth that they want in the glacier. Well, this is Lonnie Thompson, a glaciologist. This is one of those ice cores here. Here's the drill. And there's Lonnie looking at what just came out of the ground. And they take these things and put them into special containers, and they're put into deep freeze things. And what they're measuring is something that looks like a cutaway of this. This is an ice cap in Peru, and looks a lot like tree rings. Well, what they can do is, here's your ice core. Here's a microscopic scattering microscopic view of air bubbles that are trapped in the ice. So what they do is they cut off a calibrated amount of the ice, put it into a vessel, make a vacuum, melt it, and then anything that's in the air bubbles is then measured. And they can do some rather interesting instrumental analysis of this, and one of the things that they can measure over time is that they can measure things like carbon dioxide that's in the air bubbles. This is an 800,000-year-old ice core data that shows pretty good, variability, ice ages that we can have. The things that make these peaks and troughs they're called Milankovitch forcing. If you've got about 3 lecture periods, I can explain what they are in terms of how the Earth rotates around itself on its axis of how the Earth rotates around the sun, because the orbit is an oval, but the oval can sometimes tilt, it wobbles, it gets shorter, it gets longer, and the axis of the Earth can actually, move around. Well, they have 119-year cycles, 40,000 year cycles, 18,000 year cycles that they measure, and when they superimpose, they can come up with maximums and minimums and maximums that correspond quite nicely to ice ages. So they can also do some things about measuring ratios of oxygen that give a pretty good indication of what the temperature is like. So we see some corresponding similarities here. If we take a look at where we are in 2008, just a few years ago, we were at about 388 parts per million. Just this past year, we finally exceeded that amount that goes up to 403 parts per million. And eventually, there's supposed to be a line that goes all the way up to here. On my 100th birthday, we may be somewhere around 550 parts per million. And you have to remember that this baseline here never got above 300. When they started measuring in Mauna Loa, they were probably right about here at 315 parts per million in 1956 and 57. Here's global surface temperatures again, showing a record that's been done by calibration with real temperature values. They do you'll see the high points and low points, and they do what's called a curve smoothing, where they take usually a 5-year average. This is what's up here. They'll take 5-year averages and take that number, do the next 5 years, take that number and plot it, and it just sort of like averages out some dampens the thing, gives a better rendition of what the trend may be on a short term. This, by the way, these slides come from the 2014 National Climate Assessment document that was sort of unveiled late spring. Here in the Northeast, we can see that our temperature change from 1991 to 2012 has increased. Here we are in Rochester. Here's the Adirondack region. And yes, there are places where it's a little bit cooler than it was, not too long ago. But you can see the trend is for the United States is that there's a general warming. It's interesting to note that this portion of the country, sort of like the northern tier, may be the portion that has seen the greatest extent. We can do all sorts of things about measuring our frost-free season. That is the number of days that we have without any frost. In the Northeast, we've added 10 days, and people say, well, that's not 10 days. Is not even a 2-week vacation. But it means an awful lot to growing seasons and farmers who have to contend with things, and it has an awful lot to do with pollination of plants and such. Well, one of the things that people always want to say is, well, how much of this is natural, how much of it isn't? This shaded area is sort of like a greenish kind of a shaded area here. If you run a climate model and take into consideration all of the variabilities that are of a natural nature in terms of volcanoes, natural emissions of CO2 that come from volcanoes that are influenced by solar influences, and all the sources from the geological and chemical processes that take place over about a 1,000 or 100-year period of time. That's what we get in this color pattern here. Well, if you run that same thing and start throwing in all sorts of natural and human factors, such as the burning of fossil fuels from various sources, taking the land use changes, how we contribute to changing carbon dioxide levels by what we do in terms of housing developments, deforestation, changing from in the United States, a lot of our agricultural land is now suburban lands or cities. That's the blue area. And that's just a theoretical or hypothetical model. This is the one to take a look at, is our observations over time and being able to come up and say, here's the global temperature, and see how that overlays with what the models have been predicting. So we're actually coming up to the fact that we've got some data that sort of indicates that the models may not be that terribly wrong. Some people would want to argue, well, it's urban heat island. We've got more cities that are doing, and so the heat's going to get captured. Everybody knows what it's like. It's a couple of degrees warmer. In the city, the metropolitan area, the city on a really hot 94-degree day in the city might be a 93 or a 92-degree day down at the airport. When you start plotting these, you find out that the trends stay pretty much the same. Regardless if you're talking about a rural, suburban, or an urban area, the trend lines are pretty parallel, indicating that, well, if it's going to be 2 degrees warmer, it's going to be 2 degrees warmer regardless of where you are. Sunspots cause, well, yes, they contribute to the overall thing. It's part of that natural variation, that background. But when we take a look at temperature and CO2 levels, and the amount of influence that the sun is going to have from 1860 to the year 2000 and about 2005, we see that our contributions of carbon dioxide may be a bigger driving force than the solar influence has. Probably less than 10%, and perhaps if we take a look at some of this in here, it's maybe 1 or 2% less today than it was just about 15, 20 years ago. Yeah, sunset, sunspots, and solar activities do have an influence on climate, but we are dwarfing that natural background by what we are adding. We're enhancing the effects. Volcanoes. You hear something, oh, it's volcanoes. We have all sorts of volcanic eruptions. Well, if we take all of our human contributions from the burning of fossil fuels and land conversion, this blob here is what comes from volcanoes. And some people say, oh, it's just amazing how much is spewed forth by volcanoes every... Here's the temperature, here's the carbon dioxide, here's the volcanic eruptions. What do we see? Sometimes we see cooling effects. That's because of the particulate matter that comes up there. This is Pinatubo. One of the great scientific findings of meteorology was when this thing was shooting up a plume that went about 60 to 70,000 feet in the air, it had an incredibly huge sulfur content. And that found out that when the sulfur, mixes with the clouds and creates sulfur dioxide, the clouds are whiter, they're brighter, the albedo effect is greater, and the reflectance is greater, so it was actually reflecting more sunlight back into space. So we see, perhaps between here and here, this portion of this curve is a little bit lower than it was over here. The temperature drops. El Chichon drops. Agua drops. So you've got a combination of chemistry and particulate matter that says it's not contributing anything to carbon dioxide, but yes, it does affect climate. The temperature hasn't changed since 1998. True. If we take a look at the graphs that I've shown you, you see that we get up to about 1998 and the variability stays pretty stable. Here's the temperature of the land. Take a look at what's going on with our oceans. This is land, ice, and atmosphere here. The ocean content from 700 to 2,000 meters and from 0 to 70 meters. We are adding an incredible amount of heat energy to our oceans. And when you consider that we're raising the level of the seas by maybe a foot in most of our lifetimes, 6 inches to a foot, that's an incredible volume of water. So we're heating a larger volume of water, taking out more energy and doing all sorts of things with, again, physics and chemistry will come back. This is an interesting series of graphs. If we take a look at plotting, the summer temperatures have shifted cooler than average, or warmer than average. This is what a 30-year history shows from 1950, and take a look at what's going to happen over the next couple of years, from 81 to 91, 91 to 2001, and 2001 to 2011. This shift to the right is indicating that this bell-shaped curve is moved where we're having more warmer than average and extremely hot days are coming down over here. So we're shifting our climate over here to a baseline of 1951 to 1980 as the mean. What used to be the extreme temperature events of being, and I don't know why this is coming out fuzzy other than the fact I know it's a shadow on a font. It used to cover about 1/10 of 1%. It's now 10% of our time is spent with extremely hot temperatures. How hot? The next series of slides I'm going to go through rather quickly, but just take a look at the locations of where some of these are and some of the numbers that are coming in here. We rarely get this hot in Rochester, New York. Yeah, thank heavens. But when you think about some of the places that I'm showing you here, some of our troops in Afghanistan, people who have been in Pakistan or Iran, have had to carry 90 to 100 pound packs in full gear and stuff. In China. Australia actually has had to add 2 colors to their maps to indicate how hot it is, beginning in January of last year. The heat waves that are now presently happening in Australia are estimated to be 5 times more likely, and the cause is being attributed to carbon dioxide. I have a friend of mine I went to high school with who thinks that this is all really all hoax, fraud, bogus, whatever. And I told him once, I sent him this picture and I said, I said, it's a lot more complicated than going outside and sticking your, wetting your finger and sticking it up in the air and saying, oh, the wind's coming from the northwest today, so oh, wow, the wind came from the south yesterday. It's colder than it was yesterday, so where's the global warming? It is a lot more complicated than just making those casual observations, whether they're in your backyard in Rochester or outside of Colorado Springs. When I did my training, this is the Earth's atmosphere. This is the Earth right down along in here. This is just the sun coming up over top of the Earth rim is right here. We were told that if you took about an 18-inch globe and put a layer of varnish on it, that represents about the thickness of the atmosphere. And it's inside this thin layer that all living things are, and will be supported on this planet. So how does this contribute to global warming or climate change? Well, let's talk about the warming effect. Now, I gotta go stand over here. Remember that molecule I showed you before about carbon dioxide? Right here's a good spot. Carbon and oxygen, okay? 1 molecule of carbon, 2 molecules of oxygen. Well, if you remember from your high school physics or maybe even junior high physics that certain chemicals, when you excite them with light, they get a little agitated and they start getting, infrared radiation with carbon dioxide just sucks it right up. And those molecules start vibrating because of physics, and they end up gaining more and more energy. Okay, the electrons are spinning around and the oxygen's doing it and everything's getting really hectic. And then when that energy is released, it's released as heat. So the sun, which represents that light there, and this is carbon and oxygen. When it strikes the Earth, it illuminates things. It gives us, our daylight and our such. But some of the energy is actually radiated back. That's how come you can go to the moon and see the Earth rise. That's how come sometimes if you look at the crescent moons, sometimes you'll see a really, really faint blue outline of the moon. It's not an optical illusion. What you're doing is you're seeing Earth shine coming back to Earth. The Earth shine is hitting the moon, coming back to you as that very, very faint glow. That's the remnants of what was radiated back into space coming back to us. And you can see it. Well, some of that radiated energy goes back out into space. It just is lost. However, a certain portion of this is actually staying with us within our atmosphere. It's just being re-radiated. It's not only carbon dioxide, it's methane, it's oxygen. Water vapor is probably one of the largest trappers of energy from the sun. And this little layer here of this atmosphere captures where all of this dramatic play is taking place. So we come up and find out that, this greenhouse effect, we go back to the early 1800s when they began describing some of the physical properties of carbon dioxide, and the greenhouse effect being described in pretty decent detail in the late 1800s. And what happens when we have carbon dioxide around various types of planets? Here's the Earth and Venus. The Earth has a certain amount of an atmosphere that has a certain chemical composition of carbon around it. Venus is much, much more dense with carbon dioxide. We stay at about 15 degrees centigrade, which is about 59 degrees Fahrenheit. It's about 800 and some odd degrees Fahrenheit. You say, well, what happened about this little thing called Mercury? Well, Mercury's a lot closer to the sun, and it's cooler than Venus. Why? There's hardly any carbon dioxide in its atmosphere, so you're just getting the heat. It's coming from that. None of it's being actually retained or concentrated as it is in Venus. Oh, by the way, Mr. Gore loves this slide. He calls it the Goldilocks slide. You know, if you put Mars on here, Mars is colder. It's colder. This is, you know, it's warmer. This is way hot. And this is the Goldilocks. That's why we have a stable kind of place where we can live. It supports life just where we are. This is life-sustaining portions of maintaining that 59-degree plus or minus a few degrees. We can tolerate differences. I mean, we survived when it got colder, and we survived when it was warmer, but we're adding an awful lot of stuff in the atmosphere to change those parameters of what's going on. This slide, actually, I was looking for it earlier, but I wanted to move it someplace. When I first started doing these presentations, we were just taking a look at, hypothetically, some of this data actually comes from the early 2000s in terms of saying that these are the areas along Long Island and Connecticut and New Jersey that were susceptible to increased sea level erosion, coastal zone erosion. Joe Bastardi, the chief forecaster for AccuWeather, plotted these things about saying, here are some major hurricanes that have impacted this area of country. And said, you know, 10, 15 years ago, the Northeast is staring down the barrel of a gun. It's long overdue for a powerful hurricane. And with the weather patterns and the hydrology we're seeing in the oceans, the likelihood of a major hurricane making landfall in the Northeast is not a question of if, but when. We'll see some slides that shows what happens when Hurricane Sandy came up here. Hurricane Sandy was not a powerful hurricane. It lost its level 1 status a couple of minutes after it made landfall to a tropical storm. And we all have memories of what it looked like. We also remember from a couple of falls ago, geez, this was just a year ago, almost. Super Typhoon Haiyan. One of the largest typhoons recorded in the Pacific in many, many years. And I'm sure that you can remember similar kind of rain events. Maybe not, because we don't see this in our paper. The Democrat Chronicle doesn't carry these. This is one in Pakistan where 20 million people were affected by flooding. It's pretty devastating when you consider that one of the ways that they may be able to, at some point in time, get themselves out of the jam is that it's a nuclear-armed country. But 20 million people affected in Pakistan in 2010, that's a sizable amount of displacement of people. This is Beijing, China. I'm just going to go through these slides rather quickly and say, I want you to take a look at where some of these storms are taking and when. They're coming from all over the world. They've happened mostly in the past 5 years. They are catastrophic flood events, sometimes with enough warning because we can warn people ahead of time that there's major storms coming to prepare. And sometimes that message is prepare for the worst and do the best you can. We'll see you in 3 days and good luck. So we even see places where you don't normally associate with floods, these catastrophic kind of floods taking place. But nonetheless, they are catastrophic in nature. And some of them are on this side of the world, others in places where we may have gone on vacation. Some of them may represent places where our ancestors or came from. Talk about a kayaking experience. Where's that ADK meeting? You know. Well, maybe it was done in Emmersdorf in Austria. Well, things do happen close at home. And there's an awful lot of things about the flooding of the Mississippi that I don't go back much further than 2010, that we could post some other things that happened well before that. Most of us, again, again, because of the color or the lack of hair, indicate that you probably remember Hurricane Agnes in '72 that almost wreaked some nasty things in Rochester. This was the kind of thing, I was dating that young lady down there, and I was working up at Lake George in the resort area, and like 90% of our customers couldn't get to Lake George for their vacation because the roads in front of their houses didn't exist anymore, and they couldn't get there, or their houses didn't exist anymore, and they needed other more important things to do than spending a week or two up on vacation in the Adirondacks. So I left. I said I just didn't want to be under there, so I had other reasons why I wanted to leave, but I came to Rochester actually I hid out with my grandparents in Gloversville, New York, and my grandfather and I went, the last times my grandpa and I went fishing up on the Great Saginaw, what's called the Great Saginaw Lake. Back then it was just the Saginaw Reservoir. But Donnie brought me down here, and I saw Mount Morris Dam. And you can stand there and you look down there, and there's the Genesee River, and you're saying, like, why the hell would you want to build a dam if you're not going to, have it go? Well, if you look right across, you can see the mud line where there was, I think it was the second largest man-made lake in the country. This is when the results of Hurricane Agnes. And Donnie had some of the newspaper clippings that the engineers did this. Well, we think it's going to hold, and fortunately it did. I mean, we'd probably still be picking up pieces of something. But we've had these catastrophic floods in Canada and Scotland and Sweden and England and all over the place. So as global temperature continues to increase, so does our water cycle change, because we can evaporate more water faster. We've increased, and you're talking about some of the impacts that we see. Just minor changes can have catastrophic kind of consequences. We've increased the amount of water vapor, and so the water vapor content in the atmosphere is about 4, maybe 5% at the tops. Let's say 4% higher than it was 20, 30 years ago. Well, you put 4% more water into the atmosphere, where's it going to go? It's going to come out. It's got to rain out. It's just not going to stay circulating in the atmosphere and say, oh, we're just going to, the status quo, you're going to get 9.8 inches of rain. And you take a look over the past 20 years, Rochester's getting now about 9 inches more rain per year. I don't have the data here. We still have about the same number of snowfalls, except that the ones that we get from Lake Ontario or Lake Erie are a little bit more frequent, and they're a little bit deeper than they sometimes, on the average, can be. I've got a really interesting slide back that I'll show you about sort of like an extreme. Okay, so what happens is we have these rainstorms that